Hi everyone, today we're going to be looking at the ProductivityOpen P1AM Industrial Arduino P1000 Expansion Digital Inputs and Outputs Part 2. Now in Part 1 we added additional discrete inputs and output modules to our P1AM-START1 Productivity Starter Kit with Ethernet. So the first thing we'll do is we will actually take a look at our hardware, and last time, as we mentioned, we've added our 16 relay output. We added a combination 8 in and 8 relay outputs. That's 8 DC in, and then we added our 8-point simulator input module. So there are cards that we added to the actual unit. Now today what we're going to do is take a look at some additional features that we can do with these cards. Now detailed information contained in the video can be found at accautomation.ca. A link has been put in the description below. If you have not watched the other videos yet, there will be links in the description below that will start you at video 1. There will be links to the rest of the videos in the series as well. So when we look at our hardware, again, as we discussed before, we look at the addressing of the hardware, and this is slot 1, 2, 3, and 4. So everything in our ProductivityOpen consists of, and when we do expansion, consists of our slot number and point number. And the point number represents the individual points, such as my simulator here, which is slot 4, and then we have point 1 to point 8, because we have 8 switches on this unit. So that's how we address the digital I/O itself. Now, one of the features is on ProductivityOpen is the ability to use productivity blocks, which it makes programming quite easy and automatically converts everything that we do here into C++ code, so we do not have to worry about syntax. So let's take a look at an additional instruction that we had. Now last time what we did, we used the P1IO, and we used the blink, the get points, set points, and then get point and set point, so for individual points and for the entire channel at one time. And then we used also the blink. Today let's take a look at another instruction that's very important when we talk about expansion on the P1AM, which is the roll call. Now what the roll call will do is we can add, as we mentioned before, up to 15. So that's why we have 15 different items here and names. And then we put the number of modules that we have. In our case, we have 4. And now we can actually list the P1 modules that we have in our rack. In this case here, we'll add 4 racks. So what this will do is on the roll call, it will tell us if we have all those modules and in the correct sequence. And if it isn't, then it gives us an error or gives us an indication that there's something wrong. So that is the roll call. So we're going to put that into a sample program. All right. So let's call up a sample program that we have here. Here we go. And that may look quite busy, but it's really quite simple. So the first statement here is the true. So we're using the P1 modules. Then on our setup, we're going to go to subroutine initialize. And what we'll do is take a look at that subroutine initialize, which is right here. So we're going to set our previous milliseconds to 0. We're going to set our CPU LED to low. We're going to set our points to in slot number 2 to 0, which is our relay output card. And then we're going to set slot number 3, our outputs, to 0 as well. So we're going to 0 those outputs to make sure they're actually off. And then we're going to take our shift register and we're going to set it to 0. And what we'll be doing in this program is using this first card as a shift register to shift the bits down and up on that card. So that is my initialization. Next is my subroutine check P1000 expansion module. So let's go to that subroutine, which is right here. So there's my subroutine check. and I have a condition on that. And so while we have the roll call, and it is not equal to 0 right here, then what we're going to do is we're going to blink the LED pin on our processor. So this LED pin here is going to blink if our roll call or the information is not identical to what we have set here in these modules. So there's my first module, which is my analog, then my relay output, 16-bit, then we have our combination, DC inputs and relay outputs, and then we have our simulator. So if those modules aren't present, those 4 modules in the right order, and if they are, then it'll return 0, so it will be equal to 0, so that won't activate. If it isn't, then that will activate and we'll be stuck in a constant loop of blinking that LED, so indicating there's something incorrect somewhere. So next what we'll do is we're going to check for our CPU switch. Now our CPU switch will determine whether or not our program will run or not. So we're going to use that LED light right here. So when it's on, it will be lit like it is right now, indicating that our program is running. If we have it off, then we want to make sure that we indicate that the program's off. And as you just saw, if our roll call is not correct, we are going to blink that LED. So check for the switch. If the switch is high or on, then what we're going to do is we're going to take a look at slot number 4 and get all the points. So we're going to call this up a long variable called slot 4, which is my simulator input, and we're going to get all those points from that simulator input into our variable called slot 4. Next, what we're going to do, if the switch is high, is we're going to do a stop-start circuit. So switch 1 will be my start, switch 2 will be my stop, and I indicated here that my stop is normally closed. So all these conditions here may not make a lot of sense. However, what we do is we take slot 4, which is my input variable, and we AND it. So this is a bitwise AND with the number hexadecimal number 01, which means that the first bit's going to be on. So as a review, if I take a look at my AND statement, if my first operand is 0011 and my second is 0101, and I AND those two together, 1 and 2, then only when both are 1, it actually passes a 1 here. So if we set the mask as being a 1 and the input is off, then it's going to produce an off. If the input is on and I set a 1, it'll produce a 1. So looking at this, what we do is we say if slot 4 and 1, so it masks out all the other inputs and only looks at this first one. If that is greater than 0, so it's on, and we have slot number 4 and the second input is greater than 0, so that is my stop. So there's my start, stop. Then what we do is we set our point, which is slot 3, point number 2 to high. So slot number 3, 0 or 1, 2, 3, and the second input or point right here will be then turned on. Then what we do is the condition to turn off our stop would be actually the same stop switch. So if we have slot number 4 and number 2 is not equal to 0, then what we do is we set the point to low or off. So that is our stop, stop, start, stop. And we can actually simulate that right now. So if we were to say that switch number 2 is on, and then we turn on switch 1, which is a start, then the output Second output here now turns on just like we expected. If we turn off the start, you can still see that our output is still on until we actually stop it. And then we can turn that stop back on, waiting for a start again. So that is a simple start-stop circuit using the industrial Arduino and the I/O from the P1000. Next, what we'll do is take a look at some shift registers. So let's look at the shift. And we're going to shift 16 bits on channel 2. So the first thing is we look at slot 4, and we're going to look at 80, which is the very last switch here. If it's not equal to 0, if it's equal to 0, then what we're going to do is we're going to set our shift register value to 1. We're going to set our points. So we're going to set slot 2 to a shift register. Remember, shift register contains 1. And then we're going to set our Boolean shift left to high. So this is my shift register. You can see now that I've set the first one to 1 because our switch is off. Then what happens is if we're shifting left and the condition is that the runtime minus the previous milliseconds is greater than or equal to 500 milliseconds, so half a second, then we'll set our previous milliseconds to our run milliseconds. So we did this in our timing before in our previous post. We'll set our point 2 to our shift register, and then we take our shift register and we shift it to the left by 1. Then if our shift register is equal to 32,768, which is the last bit of that shift register, of that the 16 bits, then what we do is we set our shift left to low. Now, remember here, if our shift left is high, we do this. If it's low, then what we do is we basically do the same thing. We delay for 500 milliseconds. Then we take our shift register and we're going to shift it right by 1. And we're going to shift it right by 1 until we hit the number 1 on our shift register. Then we'll shift left back to high again. So what we do really is just take it and shift it left until we reach the end bit, and we shift it back up again. So let's just try that out, and we can turn that on. And when we do, what you'll see is our bits are shifting all the way down to the 16th bit, then back up. So we're shifting right now. And then when we hit the top, we shift left again, going back down or through the bits again. So that is a shift register. And if we turn it off, it goes back to 0 again. So finally, then next time, if our CPU switch, again, if it's set high, we do this. If it's set low, then we set our subroutine initialize. And the subroutine initialize, once again, will do the following. It will set our previous milliseconds, so that sets the shifting of our shift register. It will set the CPU light to low. It will zero out our output points, slot number 2 with value 0 and slot number 3 with value 0, and it zeroes out our shift register, so 0 itself. So again, if I turn this off, you can see that my shift register goes off and all my outputs actually turn off. Then at the very end of the program, at the end of the scan, so is once we checked for our condition here in our loop, the last thing we do in our loop is check the expansion modules. So once again, we are checking using our roll call and ensuring that we have our 4 modules still in our rack and everything's functioning well. And if it isn't, then what we do is we call up an alarm. So once we have our program, and what we're going to do is we have this program already in the controller, but let's go ahead and we'll verify that just to show you what it looks like in our IDE. So here's my roll call. You can see that I set up a string and I compare on that. Then we can upload this to the controller. So just as I explained, now everything that we see in there is now into controller, and we can actually then put this program through our spaces. So right now I'm off, and remember my power light is on, indicate I have power. My base light is on, indicating I have power to my expansion modules, and my LED light is off. That indicates in our program that we have everything okay and that the power is off or our program's not running. If we turn this on, then our light comes, LED light comes on, indicating our program's running. My shift register first bit is on. I have my start and stop signal, so let's go ahead and turn my start on. Turn that off again, and you can see that my output here will now turn off. And then what we'll do is let's start our shift register. And on my shift register, my LED is going up and down as it should, as we expected. If I were to turn this off, you can see that everything goes off. All my outputs are off, and then when I turn it back on again, I pick up where I left off. So again, I have to reset my shift register, and then we'll start that again. There we go. And you notice that my start stop, I have to start it again. So the last thing we have to check in our program is the fact if we remove power. So let's go ahead and what we'll do is turn this off. There we go. And you can see we turn it back on. We have the run light. Let's remove power to the whole unit. And what we'll do is let's take off our simulator. So our simulator is no longer connected to our system, and we'll plug this back in. And here we go. And just as we expect, we have our power light. We have our base light indicating that we have 24 volts on our output module or our expansion modules. But we have our flashing LED light now, and none of our outputs are actually lit or could be lit because we have this indicates in our program that we have an error that our roll call did not pass, and we're stuck in an endless loop of blinking our LED light. So again, let's take off the power. Just gonna make sure you don't want to connect and disconnect cards under power. We'll plug our expansion unit back in, snap it down. We'll plug this back in. We'll allow it to boot up. And when we do, you'll see that again our LED light turns solid, so everything's working correctly. So if you enjoyed this video, please hit the like button below. If you have any questions about the video, please leave a comment below and I'll do my best to answer it. If you want any more information about us or you want our free ebooks on numbering systems or robust data logging, please click on the link in the description below to get it. A new video is put out every Monday, so make sure you hit the subscribe button so you get more videos like this in the future. Remember to click that bell beside your subscription to actually receive those notifications. Thanks so much for watching. I'll see you next time. Stay safe.